announce the first speaker of this afternoon session. It is Paul Matthew, and he will speak about exponential integrators, the computation of the exponential.
Okay, thank you. So I'd like to do three things. I'll start with a fairly simple introduction to exponential integrators and what we call exponential time differencing methods, which will be very familiar to some people in the audience, but perhaps not to everybody. I'll give a couple of examples of application of these exponential methods to some highly oscillatory problems. And then I'll talk a bit about a comparison of some different methods for evaluating certain coefficients that appear in these methods. So by way of introduction, we're interested in solving semi-linear PDEs, so non-linear PDEs, such as Navier-Stokes, Kurimoto-Sivashinsky, K to V, etc. All sorts of interesting PDEs that people are interested in have the property that they're semi-linear. In other words, the leading spatial derivative term appears as a linear term. So when you do a spatial discretization using either a spectral method or a finite difference method, you end up with some large system of ODEs. So typically, if this is our original PDE, we take a Fourier spectral method. So n represents the nonlinear terms. This represents the leading derivative in the linear term. And in the Fourier space, we get a system of equations, something like this. And this system of ODEs is stiff because we have a wide range of spatial wave numbers raised to some power. And the stiffness is predominantly due to the linear term in the PDE. So that means that if we were to use a straightforward explicit integration method, then our time step would be limited by this stiff linear term for the highest Fourier mode. So an explicit method would need a very small time step, h. Of course, we could solve this problem completely implicitly, but that's often quite slow because we have to do a complete nonlinear solver at each time step and so on. So it's better when solving these sorts of systems to solve this stiff linear term either implicitly or exactly. So let's suppose that we've done our spatial discretization, reduced our PDE to a system of ODEs of this type. So C represents the linear terms, F represents nonlinear terms in the system. And if we're talking about a dissipative PDE, such as Kurimoto-Sivashinsky, then this matrix C will have some large negative eigenvalues. If we're talking about a PDE such as KdV, then the matrix C will have large imaginary eigenvalues in the oscillatory case. And F represents the nonlinear terms or some forcing terms. So I'm going to briefly describe three types of methods for solving this system that get around this problem of the small time step. So the first approach we might try is what's called the linearly implicit method, where we solve the linear term implicitly and the nonlinear term explicitly. So it's sometimes called IMEX or semi-implicit method. So the simplest method of this type would be to use backwards Euler on the linear term and forward Euler on the nonlinear term. So if you do that on our toy equation, u dot equals cu plus f, we end up with this formulation, which is called the first order linearly implicit method. And this implicit part that uses the backwards Euler is astable, so it's stable for any step size h. So this method works quite well, provided that we're on the slow manifold. So of course, if we've got our equation u dot equals c times u plus f has a slow manifold, and then solutions that either oscillate around that slow manifold if c is complex, or converge exponentially onto the slow manifold if c is real. If we're on the slow manifold, this method works quite well. If we're off it, it doesn't, because of course it completely fails to capture the rapid oscillations or rapid exponential decay. Another weakness of this method is that we can't extend it to arbitrarily high order. We can easily extend it to second order, but there's the Dahlquist stability barrier that says that we can't have an astable method beyond second order. So we can easily extend this to second order, but not so easily beyond second order without losing this stability. So then the idea of exponential integrators is to say, well, this is all very well solving the linear term implicitly, but why do that when, of course, we can solve a linear equation, we can solve the linear term exactly. So that's the idea of an exponential integrator. And the way I see things, there are two types of exponential integrators. The first one, which I think is due to Lawson 67, which I'll call the integrating factor method, where we just multiply through our equation u dot equals cu plus f by an integrating factor, and then essentially just make a change of variable, and then time step this equation using, say, forward Euler, and that leads to this method here, which gets around the problem of the small time step. We can extend this method, so this is the first order forward Euler type method of this type. We can easily extend to any order, so we can apply whatever numerical method we like to this system. And it gets this fast exponential behavior exactly correct, so it solves the linear part exactly. But in fact, this method is not very good. This method has a number of disadvantages. So what we've done here is introduce this rapidly varying timescale, eta minus ct, into this nonlinear term f, which is a rather bad thing to do, and that leads to large error constants, so error constants that scale with this large parameter c. And that leads to large error constants and very poor behavior on the slow manifold. Another, well, in fact, closely related weakness of this problem is that it gets the fixed points wrong. So we had an interesting talk from Renu Crispel a couple of days ago on methods that preserve the linearization, but this method doesn't even preserve the fixed points, so has no chance of preserving the linearization because it gets the fixed points wrong. So that's a serious problem for nonlinear systems. So this is really not a very good numerical method. It appears in various books in the context of spectral methods, and in particular, for example, Boyd's book points out that this method does rather poorly on the slow manifold, but gets the exponential behavior correctly right. Gets the exponential behavior correct, whereas the previous method, the linearly implicit method, is kind of the other way around. It does rather well on the slow manifold, but just badly off the slow manifold. So a better method is what I call the exponential time differencing method, which goes back to Certain in 1960. I'll say a bit more about the history in a moment, which says that we do the same thing of multiplying our equation through by an integrating factor, but then instead of just time-stepping this system, we write down the exact solution formally of this using the so-called variation of constants formula, and then we approximate this function f as a polynomial in t, and then do this integral having approximated this as a polynomial. And if we, in the simplest case, if we approximate this function f as being a constant, we get this first order method of this type. So this gets the exponential behavior correct. It also preserves the fixed points and does much better on the slow manifold than the integrating factor method. So this method is good on the slow manifold and off the slow manifold. And again, we can extend this method to any order using multi-step methods or Runge-Kutta methods, just by improving the way we approximate this function f using information from previous steps. Right, so this method does not appear very often in the textbooks, so I have to be careful what I say here. There's many excellent textbooks written by people in the audience on methods for differential equations, but they tend not to describe this method, and the only one I found is the one by Miranka that actually describes this method on the previous slide. It's been reinvented many, many times, and of course this happens all the time in science, that people reinvent the wheel, but this is one of the most spectacular examples I've come across. So actually looking through the history of this method is very difficult. You can't just Google something because you don't know what to Google, because everyone who's invented this method has given it a new name. So here are some of the names that people have given, and some people don't give any name at all. They just say, oh, we do this. So here are some of the names. It's called being called exact linear part, exponential propagation, quasi-steady state method, pseudo-steady state method, slave frog method. It's been given all sorts of names. The reason we chose to call it exponential time differencing was because that was what at that stage, the only examples we found of this method were in computational electromagnetism, where they call it exponential time differencing. So that's why we called it that. What it should really be called, I think, is Surtain's method. So there's a paper by Surtain, who was a nuclear engineer back in 1960, about the solution of ordinary differential equations with large times constants. And he went through the stuff on the previous slide about approximating how we approximate the nonlinear term and develop multi-step methods of this type. It was then one of the first reinventions was by Siebert Norseth, who gave very nice formulas for constructing these multi-step methods of this type using generating function. There's an interesting paper that unfortunately is in German from a conference proceedings, so I think we could be forgiven for not knowing about that one, which actually develops Runge-Kutta methods of this type. There is a paper by Hochbrook, Lubitsch, and Sellhofer, which takes a slightly different approach in that the idea of that their paper is more where we take really linearize each time step and compute the exponential of the Jacobian using Kridov subspace methods. Whereas the approach that I'm thinking of is where we take a fixed linearization and work with that fixed linearization throughout. Our paper really just made the rather simple points of these different methods and showed some comparison of simple examples of ODEs and PDEs to show that this method was really one of the best methods available, and that was confirmed by Kasam and Trefethen. There's a nice MATLAB package from the people at Trondheim, and a review paper which you can download off the web, but unfortunately it's not been published. I think the referees didn't like it, but it's been cited a few times, this review paper, and it's quite useful to looking up the history and the so on. So I suggest rather tentatively some definitions. So suppose we have this simple equation u dot equals c times u plus a nonlinear term f. Then an exponential integrator should be anything that gets the linear part exactly right. So an exponential integrator would be anything that gives the exact solution to that system when f equals 0. But these other improved methods where, due to Surtain or the exponential time differencing methods, have the stronger condition that they're exact when f equals constant. And because they're exact when f equals constant, that requires them to have this factor here is therefore inevitable in these sorts of methods. So there's some suggested definitions. A couple of examples then. So we've heard a lot about the KdV equation. So here's an example of testing these methods on the KdV equation. Of course, KdV equation has many different types of solutions, many different regimes. So we tested just a simple soliton solution, the Sech squared solution, with relatively large amplitude with this constant c, and follow one period of this soliton with periodic boundary conditions. And looking at these different types of methods, and when we look at compare second order methods, we find that the exponential method is better than the linearly implicit method, which in turn is better than the integrating factor method. When we look at the fourth order methods, so we compared a Runge-Kutta method of this exponential time differencing type compared with the integrating factor type, and the ETD type was considerably better. The Li methods, as I said before, are unstable for fourth order. So here's a picture to show that. So this is relative error against step size h. Here are some second order methods. So some two linearly implicit second order methods, one integrating factor method here, and the exponential time differencing method here is the best one. And then for fourth order methods, two fourth order methods here, an integrating factor fourth order method here, and the exponential time differencing fourth order method here, doing rather better. Just by way of providing a few pretty pictures, I thought I'd mention a more complicated application, which is convection in sunspots, which is something which I used to work on with Mike Proctor and Nigel Weiss in the building next door. So here's a picture of a sunspot, region of a strong magnetic field coming out through the surface of the sun. And this can be highly oscillatory in some regimes. So we study convection in a layer of fluid heated from below, permeated by a vertical magnetic field. So these arrows here represent the magnetic field, and these loops represent the convection cells. And so you have to solve a couple of equations, which I won't write down, Navier-Stokes equations, equation for the magnetic field, and equation for the heat transfer, all coupled together. And if the field strength, measured by some parameter Q, is large, so in other words, we've got a very strong vertical magnetic field. Magnetic field works like a kind of, think of it kind of a string of elastic bands going through the fluid, and leads to some rapid oscillations. And so convection is actually rapidly oscillating if this field strength is large. So that's an example of a highly oscillatory system. Here's just some pretty pictures from that research group's webpage, illustrating the sorts of interesting solutions you can get. These are, I think this picture shows the strength of the magnetic field, and this picture shows the temperature in a large domain. So these are using, not using any sophisticated time-stepping methods. These just use second-order Adams-Bashforth, I think. So here are some tests looking at a standing wave solution. So fairly rapid oscillations, not very rapid oscillations, in fact, in this example, with a moderate value of this magnetic field strength parameter Q in what are called the moderately nonlinear regime. So, of course, how good these exponential methods are depends on what regime you're in. If you're very close to linear, if you're in a very weakly nonlinear regime, these methods are very good indeed. If you're very, very strongly nonlinear, then they're hardly worth using because you're very long way away from the correct linearization. So here is a plot of the error in a parameter which is the heat transport in the system against the step size h, and this is just a linear plot, not a log plot. And so again, we see that these are all first-order methods. So this linearly implicit method is the least good. The integrating factor method is a bit better, but the exponential time differencing method is the best, at least on this problem in this regime. Relatively rapid oscillation. Okay, so then the third part is the slight complication with these exponential time differencing methods is that they evolve these functions that are so-called phi functions, which are defined here. So inevitably, given that definition that I gave, we have to involve functions of this type and this type, and there's this sequence of functions, and typically we need the first n of these to get a method of order n. And so obviously these functions don't have singularities at z equals 0. They're removable singularities, but they become difficult to evaluate for larger and larger n for small z because of rounding errors. So I'd like to say a bit about how we evaluate these functions, which is a topic that various people are currently looking at. So let's suppose, first of all, we just think of the scalar case. So just think of evaluating these functions for a scalar. A simple, rather crude fudge is to just use this explicit formula if, say, z is greater than 1, and to use, say, an 8-term Taylor series when z is less than 1. And that works all right. But in the case where z is a matrix, you really can't do that because typically your matrix z will involve some large eigenvalues and some very small eigenvalues. So you can't really do this. We want a method that will work in the large z and small z case effectively. So we need to evaluate these functions phi n, but I'm going to talk about the case of the fixed linearization, which is appropriate to generally to the more weakly nonlinear regime. And in that case, we only need to evaluate these functions once at the beginning of our calculation and then use them throughout the calculation. So it's not such a difficult problem as it might appear. Secondly, if we're using a Fourier spectral method, then this matrix C is diagonal, so the problem is very easy. Essentially, the matrix case reduces to the diagonal matrix, which reduces to the scalar case. So if you're doing a Fourier spectral method of some PDE like KDV or whatever, it's trivial to implement these methods. In a finite difference case or finite element methods, then this matrix C will typically be fairly sparse, and then in that case, although we tend to think of things like the matrix exponential as being dense, there's an interesting paper by Arié where he says that, in fact, the matrix exponential is also fairly sparse in some very vague sense, in the sense that it falls off fairly rapidly from the leading diagonal. And of course, that depends on how big this H is. As H gets bigger, it falls off more slowly. So I think one of the reasons that these methods are not used that much is because of the idea that evaluating the matrix exponential is very difficult, and it generates these huge matrices, but there is scope for exploiting this sort of fairly sparseness of the matrix exponential. One more comment: if we do relinearize at each step, then there's actually a little trick involving rewriting the equation, so we don't actually need to evaluate these phi functions, so we don't have to worry of these rounding errors. But in that case, if we do relinearize, we need to work out a matrix exponential, or at least the action of a matrix exponential on a vector at each time step. So we've done some tests on various methods to evaluate these phi functions on a matrix M times our step size H, and the ones I'm going to show are for a 40 by 40 finite difference matrix for the second derivative, so just the matrix with minus 2's on the diagonal and 1's above and below the diagonal in a 40 by 40 case. And so we need to implement these methods, we need to compute these phi functions of this matrix times our step size H. And we've also looked at first derivatives and Chebyshev matrices as well, which are kind of similar, but obviously, as you'd expect, the Chebyshev case is rather nastier because it has larger eigenvalues. So here are some methods for evaluating these functions. Remember, the difficulty is, firstly, you've got the difficulty of evaluating a matrix exponential, and then we've got this sensitivity to rounding errors. So the Cauchy integral method was proposed by Kassam and Trefethen, and the idea here is that we, instead of evaluating these functions explicitly, we evaluate them via a contour integral using the Cauchy integral theorem, and evaluate them around a contour, and that gets around this problem of these rounding errors. So we do a contour integral and then evaluate that contour integral numerically using the periodic trapezium rule around a circle of points in the complex plane. So this needs a sequence of matrix inverses, which makes it relatively slow. This contour needs to enclose the eigenvalues of the matrix Z, and then as our step size gets larger, the matrix itself gets, the norm of the matrix gets larger, the eigenvalues get larger, and therefore you need to make the contour larger. And as the contour gets large, then the error gets large, and I'll show that in a picture in a moment. You can show that the error scales in this way, and so when the contour gets large, corresponding to the matrix norm getting large, then this method becomes rather inaccurate. There's a recent paper by Schmelzer and Trefethen, preprint, which uses improved methods based on some kind of rational approximation on the negative real line, which I haven't attempted to implement yet. So that's one method for evaluating these coefficients. Another commonly used method for the matrix exponential is the scaling and squaring method. The idea of the scaling and squaring method is that we, in order to evaluate one of these functions, we of some argument z, we scale it down by some factor 2 to the minus m down to below some threshold, some order 1 threshold number which you choose. And then when you scale it down, you can then use a Taylor series or a Padé approximation to evaluate the function at this scaled down number 2 to the minus mz, and then you apply some squaring rules in order to scale back up to the original z that you're interested in. And there are scaling rules for each of these functions. So this first function, phi 0, is just the exponential. So this is just saying that e to the 2z is e to the z squared, this first line. And for these other phi functions, e to the z minus 1 over z and phi 2 and so on, there are similar scaling rules that you can use. So this method works fairly well. It's very commonly used for the matrix exponential. If you ask MATLAB to do a matrix exponential, it uses this method, and it uses a version of it due to Nick Hyam. Obviously, the speed of this method depends on how many of these scalings you have to do, and so does the accuracy. So each time you do one of these scaling processes, you double the relative error. So as you scale up, you're also scaling up your error. So either your truncation error from this stage or your rounding error scales up. So you don't want to do too many scalings. So the best way to do it is to use a rather high Padé approximation and choose this threshold to be fairly large to minimize the number of scalings. There are various different forms of these scaling relations that have been published recently, and we've checked that they all give pretty much the same performance. A method that I like because it's a very lazy method, so this is the lazy method. If we construct a compound matrix, so think of either z as being a matrix and I as being the identity, or z as just being a number and I as being 1. If we take the matrix exponential of this matrix, then the top row just gives us these functions, phi 0, phi 1, phi 2, and phi 3. So this is not exactly what's in these papers by Sard and CJ, but minor variations of what they've worked out. So if we suppose that we have some subroutine that we can just call to do the matrix exponential, then this is a quick and a slow but lazy way, easy to code way of computing all these functions with one call. So it's simple to use. Obviously, it's very inefficient because we're spending a lot of time multiplying 0 by 0, but it's not too bad. So I did one test on matrix Z, 128 by 128. So this is actually 512 by 512, and it still only took a second and a half. So that's the lazy method. Another method, of course, we can use is if the matrix Z is nice, is just to diagonalize, and then when we diagonalize the matrix, then we can just use the scalar case of using an explicit formula to evaluate these functions, or the Taylor series. So this is fine if your matrix is nice and diagonalizable. So here's illustration of results for various methods. So this is the error in computing this function phi 2. That was e to the z minus 1 minus z over z squared. For the function, for the matrix M multiplied by a time step, which is here called delta t. And so as we scale the matrix up, so this is just a scaling factor for our second derivative matrix. So the red line indicates what happens if you use the explicit formula. So just ask MATLAB to find the matrix exponential, and then evaluate the formula using the matrix exponential and the matrix inverse. And that it does not do very well. You see these basically these rounding errors when the scaling factor is small, and even when the scaling factor is quite large, it's quite inaccurate. This solid blue is just a straightforward Taylor series. It obviously fails when our factor h is of order 1. This method here is the Cauchy method, which, as I said, so you have to make the matrix, have to make your contour bigger as the scaling factor gets bigger, and then that leads to large errors. Even with 128 points, you can get this down by using more points. But there are several methods. So the scaling and squaring method works very well. Diagonalization works very well. And this lazy, inefficient composite matrix method also works pretty well. All methods get a gradual increase as the scaling factor increases. Okay, so summarizing, we discretize a semi-linear PDE. We get a linearly stiff system. We can solve the linear term exactly using this ETD method, which first due to Certain, which is very good for a wide variety of problems. We need to find these functions phi n, but we only need to find them once at the beginning of the computation. In the case of a Fourier spectral method, it's trivial, there's no work to do. For other spatial discretizations, there are various methods, including the diagonalization of the matrix or scaling and squaring methods that can be used to compute these functions. And lastly, I think there are quite a lot of examples of applying these methods to simple PDEs in one space dimension. I think it would be interesting to see how well these methods work on much larger scale, more challenging computational problems.
Thank you very much. Short question.
The name exponential integrator comes in. The exponential seems to be treated in a special way. Is this way called the net? Essentially, what is a somewhat precise statement for the reason that exponential integrators are called exponential?
They're called exponential because they use the exponential and do the linear part exactly. But yeah.
I wonder if that was another reason for something not understood.
I have another question. For steep problems, it's very essential to use adaptive step sizes, change step sizes.
Yes.
You didn't.
No, I didn't.
Address this.
No.
It seems that you always use constant step sizes.
Yes. So of course, if you use a variable step size, you'd have to reevaluate these functions. So one thing you might do is perhaps set up several of these functions to start with different with a selection of different step sizes, and then as you go through your calculation, use a selection of different step sizes as you adapt. Yeah.
Okay. Thank you once more.